morning, everyone, and welcome to day 2 of the Linley Fall Processor Conference. Today we have 2 great sessions for you. We have our first session this morning on vector processing cores, and then following the break, we'll be having a session on cloud AI. So right now, I'm going to kick off the morning session. Our first presentation is from Krste Asanović, who is a co-founder and chief architect at SiFive. Krste is one of the originators of the RISC-V architecture. He's a professor at UC Berkeley, where he worked to develop the architecture. And he is an ACM fellow and an IEEE fellow. Krste, welcome, and please go ahead and share your slides.
Okay, great. All right. Hello, everybody. So today I want to tell you about extending AI SoC design possibilities with our Linux-capable vector processors. So there's been obviously a lot of interest in AI in SoCs, and many applications now, SoCs want to include some AI. Today I'll talk a little bit about the challenges of integrating that in a whole system design. Especially accommodating future algorithms and the complexities of dealing with the continuing churn in new AI techniques. Then I'll talk about our solution, which is building RISC-V Vector extension and adding that to our Linux capable cores. I'll go through how that really enables you to build an efficient implementation, really helps with the software development process. Then I'll go and dive into the details about the core IP we're announcing today, the VIU7. I'll give an overview, talk about its microarchitecture and some initial benchmarking results, and I'll wrap up. So when you integrate AI algorithms onto an SoC, current solutions often include a variety of proprietary accelerators of different kinds. And the challenge here really is each of the different kinds of accelerators, GPU, deep learning accelerator, they may have their own complex memory hierarchy. They usually have their own proprietary instruction set. And judging the right mix of these engines to include on an SoC is difficult. And also actually developing this both at hardware level and at software level is very difficult. Making sure you optimize across all the different memory usages on the ASIC. So it's very difficult to get this thing optimized. And also once you built it, you may have the wrong balance for any future application workload you're running on this thing. So the software challenge is multiplied by having these different accelerator instruction sets that may have their own APIs, different software stacks. And once you come along with new algorithms appear, it's difficult to map those onto these engines, which are often highly tuned for one particular style of algorithm. And you may find, for example, a memory hierarchy is just the wrong size for your new algorithm. And typically there's poor compiler support for these custom accelerators, and there's also very poor support for stitching them all together to make a complete end-to-end application typically. So our solution is to really build on top of standards, particularly the RISC-V Open ISA standard, but also the new RISC-V Vector standard. And the nice thing for customers, if they align with an open standard, they won't have any vendor lock-in, and this should enable a much richer ecosystem for AI. Building on the vector extension, it was designed to give scalable performance from very low power, very area efficient cores all the way up to the biggest, highest performance supercomputing style engines. Not only can you scale up a single core, you can also aggregate cores to give you a multi-core complex. And with the SiFive solution, you can have a mixture of Linux capable or real-time cores mixed together in a single coherent complex. And you can scale up to multi-tops performance if you need that. By having everything integrated, you can, using the same instruction set, same memory hierarchy, you can basically all the memory hierarchy is available for any part of your code, and that maximizes data reuse, minimizes the total SRAM you need to put on the chip. And again, the single ISA makes the programming much simpler across the system, one tool chain to develop everything. I'll talk more about our software story a bit later. Another advantage of building into our existing cores is we already have comprehensive support for security through SiFive WorldGuard, which we've talked about previously in this venue, and also SiFive's advanced trace and debug solution. So a full-featured system you can get running from the get-go with a very rich support. So RISC-V with vectors really enables an efficient SoC implementation. And what I mean by that is the vector performance can be scaled up to give you very high performance to level you may not need an independent GPU or DSP. Still, there may be cases, we acknowledge there's cases where you may want the very highest performance, many teraops, and then you can integrate the accelerator as well. However, we believe we can capture more of the workloads and more of the common workloads, and particularly as you get to more complex algorithms, they may be better suited to running on the cores we're providing with the vector extension. By having a common memory system, we can share data in that cache more efficiently. We provide all the logic to handle that coherency between all the cores and also to build scratch pads, etc. And the nice thing is with the RISC-V Vector extension, you get a binary compatible platform where the library code and the code you develop can actually run on anything from a small embedded core up to a supercomputer class core. So repeating some of these points, the single ISA helps software development. So RISC-V Vectors is a vector length agnostic architecture, meaning that the code does not rely on knowing the number of bits in each vector register. So you can have very small cores with only 32 bits per vector register, or very large cores with 16 kilobits per vector register, for example. And the same binary code can run across those. With the SiFive VIU7 introducing today, it has full Linux capability, including 48-bit virtual memory support, so you can handle very large data sets. And building on top of RISC-V, you get to leverage the open source community, and there's a lot of development work going on in bringing over lots of the deep learning frameworks to run on this RISC-V Linux. And RISC-V Vectors 1.0 is going to become the industry standard for RISC-V Vectors and SIMD. So just a quick note, this is from an old paper, and it used an earlier version of the RISC-V Vector ISA standard, just to understand why we're excited about the RISC-V Vector extension. Unlike the conventional packed SIMD architectures, we're showing two here, one from MIPS, one from Intel AVX. Because the vectors can scale up in length, and because they're designed to handle a lot of the edge conditions in the hardware, you need many fewer instructions to execute a given vector loop. If you look at the last row here, the number of dynamic instructions on this simple SAXP benchmark is order of magnitude less than you need on the others. And this translates into less code size, so less static code needed, but also many fewer dynamic instruction fetches, which can reduce power. So you really reduce the instruction fetch power needed for these vectors. And this is really a modern incarnation of the classic old Cray vector style architecture, but extended forward to support mixed width precisions and the kinds of operations we need in these new AI algorithms. So today, I just give a technology preview of SiFive has been working on auto-vectorizing C++ compiler, and this is just an example of taking that little SaxP kernel, and this is the output from the SiFive auto-vectorizer. It's still in development, but already we're seeing we're getting performance that's equivalent to hand-tuned assembly code. One thing I'll note as well is that this piece of code for the SaxP will run on any vector extension, regardless of the vector register width. So you can take the same compiled code and run it on different implementations. But we're really bringing the power of full auto vectorization into the software development flow for the vector extension. So we're developing a whole line of vector intelligence cores. Today, I'll be talking about the middle core, the application core. As I said, you can start eval today on that, but we are developing a full line of vector intelligence cores, ranging from small embedded cores targeting DSP voice audio applications, all the way up to very high performance application cores, maybe suitable for example, autonomous driving, ADAS, and higher end data processing. So we intend to bring this instruction set across the whole range of core family, and also with a common software infrastructure across all these core families. So let's dive in and talk about the VIU7, the core IP we're announcing today. So this builds upon the SiFive U7 series core, which has already had multiple licensees. So this provides support for the RV64 GCV RISC-V ISA, including up to 48-bit virtual memory support. So the U7 is an 8-stage dual issue in-order pipeline. And to that, for the VIU7, we added a decoupled vector unit. But this all runs in the context of full Linux. So we have machine, supervisor, and user privilege modes with a TLB to run Linux. And we can also put these core in a single or multi-core coherent platform. We support the full vector extension for RISC-V version 1.0. It's almost finished, and we basically up to date with the current spec, and that's not expected to change. We will track that. And in that spec, we support floating point, fixed point, integer data types on everything from 8-bit to 64-bit data types. And the VIU7 supports full 64-bit double precision floating point all the way down to 8-bit integer multiply accumulates. The vector unit in this first release is one that has a 256-bit wide data path that can operate on these data paths. However, as I'll mention later, when you're performing a widening operation, it can actually sustain producing 512 bits of result per cycle. For example, you're accumulating 8-bit multiplies into a 16-bit, or doing a 16-bit floating point multiply into a 32-bit accumulator. So even though the input's 256 bits, we can actually produce and sustain 512 bits per cycle of result on this core. So it's a multi-core complex. You can configure the number of application cores with Linux. You can also add in embedded cores. This is showing an S7, one of our 64-bit embedded cores. This can be added in and be used as a boot monitor to handle security co-processing or other functions in the core complex. So the VIU7 has a private L2 cache on each core, and we can optionally add a shared L3 cache or just a coherence engine on the outside to connect the cores together. The cores also support the full RISC-V PMP system, physical memory protection, as well as the memory management unit. So you can isolate Linux from the rest of the system for extra security. We support SiFive WorldGuard security, which tags bus transactions and keeps things secure across the buses. We also have full support for the existing SiFive advanced trace and debug solutions in the system too. So diving down into the core microarchitecture. So mentioned before, we have a dual issue scalar unit with scalar integer and scalar floating point registers, 64 bits for both. And then the vector unit in this incarnation has what we say is a 256-bit wide ALU pipeline. Vector length, the registers are 512 bits wide. And so when you're executing a single vector operation with Lmul equal to 1, which means you're operating at only a single vector register, it'll take 2 cycles across that 256-bit wide data path to complete that 512-bit vector operation. There is a separate vector ALU pipe and a separate load store pipe that can operate concurrently. Operations can be chained between the memory unit and the ALUs. As I mentioned, the ALU, though we describe it as a 256-bit wide ALU, when you're performing a widening operation, it actually produces 512 bits of results per cycle. So for example, when we're doing 16-bit floating point multiply accumulate, we're producing 16-bit multiplies and accumulating those in 16 32-bit accumulators, IEEE single precision accumulators every cycle. The vector unit load store unit is decoupled, which means it runs behind the scalar unit. And load stores are up to 256 bits per cycle. Now, one of the design points here is that we designed the vector unit to run out of the L2 cache. So you can stream data directly from the L2 into the vector unit with effectively a 0 cycle load use delay. The vector operations are kept coherent with the L1, but they do not allocate in L1. And so the idea is most of your vector data set is going to live in the L2. That's your working set where you operate from. And that could be considerably larger than the L1. And this way also you don't pollute the L1 cache, which means that the scalar values can stay there and overall get higher performance. So we can initiate many outstanding requests from the vector unit, streaming out of L2 or across the memory bus to the outside world. So we have an eval systems available based on an FPGA platform with one or more VIU7 cores, the full Linux environment with debug enabled as well, and integrated into our Freedom Studio development environment. We have software support, including LVM compiler with vector intrinsics. We also have a QEMU emulation model available, as well as a System C cycle accurate model as well available. So just give you a look at how the vector unit looks inside our SiFive Insight Advanced Trace and Debug. So basically just appears, you can see the vector instructions showing up in the trace. It's fully supported, all the vector state and all the vector instructions are supported inside the trace and debug system, just as with any other instruction in the core. Some initial benchmark data. We just took a look at some kernels optimized for, in this case, we're comparing against the ARM Cortex A53. And And this is a Sobel filter, 5x5. We're seeing a 6.3 times speed up over the equivalent ARM core. For convolutional workflows, this is just looking at a 1D convolution with 16-bit fixed point. And here, because the actual performance will depend on the customer process technology and library selection, we're just showing this in terms of utilization of the ALUs in the machine. And so getting close to 80% utilization on larger filters here. Similarly for matrix multiply, we show utilizations here. And here we're varying the size of the square matrices using the matrix multiply. And the different lines represent different precisions. So half precision, which is FP16, or single precision, FP32, or double precision, FP64. So even for these very small matrices, sort of 32 elements, we're getting way above 80, 90% utilization, and then pretty close to 100% as you go to slightly larger matrices. The wider precisions, the larger widths obviously hit more efficiency earlier because they're using more of the data path, even for the shorter matrices. So finally, look at more complete benchmarks. This is Mobilenet, the MLPerf, and we're showing that the speed up here we're getting over the ARM A53, about a 4x speed up on this MLPerf application. And this is based on data that's scaled from an FPGA model running for the VIU7. The actual performance will depend on the ASIC parameters and the SoC memory subsystem that it's integrated into, obviously. This just gives an indication of the sort of performance uplift we can see on these AI workloads, complete AI applications. Yeah, it's just a fun thing to point out that when we run the Mobilenet on the FPGA, it actually runs faster than the Silicon A53 in this case. Here's looking at a great pioneer, Grace Hopper, and recognizing her image using Mobilenet. So just to wrap up here, so the idea is RISC-V vectors really turbocharge Linux application processors to handle more demanding AI processing. We have very scalable architecture, and this gives us software compatibility from small embedded cores all the way up to high performance multi-core, multi-cluster solutions. The VIU7 is the first core in the series, and it's the first RISC-V 1.0 compliant CPU core that can also run Linux. Excuse me. And with a SiFive mix and match, you can combine different cores, Linux cores, real-time cores, the same complex. And all this is integrated with our security solutions, part of SiFive Shield, and also with all our advanced trace and debug. So you can start designing today with the VIU7. Thank you.
Great. Thanks, Krste, for that presentation. And thank you for introducing the new VIU7 at our conference today. So we do have time for some questions from the audience. Again, you can submit questions using the Q&A button at the bottom of your window. So a question, does RVV support 64-bit operations?
Yes, and the VIU7 has full 64-bit IEEE floating point support.
Great. And question asking, are you saying that these vector extensions would eliminate the need for GPU cores in a RISC-V processor?
I think it depends what the GPU core is in there for. If it's for graphics, then no, you need a graphics engine. If it's for doing compute, then in many cases, yes. If you want the very highest compute, you probably need something dedicated, but then you probably would pick something other than the GPU if you were just focusing on AI in an SoC. So I think no for graphics, yes for many apps, no for the very high-end AI algorithms.
Right, that makes sense. So does RVV support 16x8 operations? I assume that means multiplication.
Not in the current RVV 1.0. No, there's no support for 16-bit times 8-bit multiplies.
Okay. So with RVV, you said there's no vendor lock-in. So the same code and the same tools would run on other cores like Andy's RVV implementation?
If they're compatible with the standard, then it should just run, yes. Okay. Obviously, there is the ISA level compatibility, then there is microarchitecture level tuning. As with any ISA family, you may schedule code differently depending on the microarchitecture, but functionally, if everybody has implemented the standard, then it would work.
Okay, so yeah, so as long as they're implementing the standard, it should work, but performance optimizations could vary from implementation to implementation.
Right.
So, okay, so another question then. So since this is based on RISC-V, is the core available for free?
No.
Okay, so SiFive is licensing the
Yeah,
cores.
the core is licensed. So please talk to us about licensing the core. Yes.
Okay. What is the availability then? Is the RTL available for licensing now?
Right. So we have a couple of lead customers already signed up. As I mentioned, the FPGA board is available for eval now. Please contact SiFive. We expect production RTL to be released early next year for production tapeouts.
Okay,
so,
great.
Yeah, we're already engaged with customers. It's in the hands of customers. We have some people signed up, and it'll be ready for production early next year.
Okay, great. Yeah, a few more questions from the audience. Is the dual issue in the core, is that statically or dynamically scheduled?
It's a true dynamic superscalar. Yeah.
Okay.
Well, it's in order dynamic.
Right. Okay. For the Saxby loop that you showed, why does the compiler use a separate multiply and add instead of a single MAD instruction?
So this is let's go back.
Somebody was looking very carefully.
Yes, this is still a technology preview. So we're working on the compiler. This is real code that came out of the compiler. That'll get combined. You may also notice it does a vector add instead of a scalar vector add. These are all optimizations that are in flight. So as I mentioned, this is just a preview, but we are seeing very good performance out of this.
Okay. Let's see. So when is GCC support expected for RVV 1.0?
There already is support for intrinsics in GCC. I don't think it's been upstream yet, waiting for the standard to be ratified, but there's a fork available that has the intrinsic support in GCC.
Okay, good. Is bfloat supported in RVB?
It will be. It's not currently standardized.
So it's not part of 1.0, but it's something for the future?
That's right.
Okay. Does RVB have any AI-specific operations?
At this point, we designed RVB 1.0 to be a very general vector instruction set to support many operations. A lot of AI is very generic operations. For example, we could say we had ReLU support, but in fact, that just means we have a max instruction or a min instruction. So we see a lot of the AI does break down into these operations. There is scope for adding considerable extra support for AI-specific operators, and you'll see that coming in future editions. But as I said, there's a lot of churn in AI algorithms, and so we wanted to make sure there's a good, efficient base that could run everything very well, rather than focusing on a few kernels we could accelerate heavily. Another thing that's in the ISA is, for example, a compress instruction, which can extract the non-zeros from a vector if you're doing sparse operations. So there's a lot of support for things you need in the AI algorithms, but it hasn't been highly tuned for a single specific AI algorithm at this point. We wanted a generic base that can run everything well as non-AI codes. There is a lot of other code, people might forget, but there is this other stuff we have to run apart from AI as well.
Okay, that's a lot of people are asking about PPA numbers, clock frequency, power, die area. Are you able to share any of those right now?
We are if you contact SiFive under NDA.
So, okay. Yeah, it looks like we're out of time. So there will be a breakout session with Krste later today. He'll be able to answer any of the questions that we didn't get to, as well as any other questions that you may have. So please join him later.
Okay,
So thank you, Krste. We'll catch you in the breakout session.
okay, thank you.